Hello and welcome to Topic 1 Math Skills. This would be suitable for a first-year algebra-based chemistry or physics class. And in Section 1, I will be covering how to convert decimal numbers to scientific notation. So, why do we need scientific notation? Well, scientific notation is needed to make very big numbers and very small numbers faster and easier to write. In other words, you're not going to have to write so many zeros. Take, for example, Avogadro's number, a very common number used in chemistry. Now, Avogadro's number would be written like this in a decimal form. It would be 602, actually sextillion, so that would be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. It would be 6.02 times 10 to the 23rd power. So from here, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 jumps to get to that decimal point at the end. All right? So you don't want to have to write this number, probably ever. Now, in physics, a very common number is the universal gravitational constant. And that would be, it's a very, very small number, that would be 0.000000, that's 6, 8, 10, 6, 6, 7. All right, so that would be 6.67 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11th power. All right, so you don't want to have to write a number like this with all those zeros, and you don't want to have to write a number like this with all those zeros ever. So scientific notation is going to make it a lot easier to write very big numbers and very small numbers. So, what does scientific notation look like? What are the parts of a number in scientific notation? Well, scientific notation looks like this. All right, there's a number with a decimal. All right, here we have 3.82. Then there's a multiplication sign, and that literally means that this is going to be multiplied by this. So it's 3.82 times, and here's the exponent, all right, 10 to the 14th. This is in scientific notation. This is what scientific notation looks like. Now, let's dissect this scientific notation. Let's see what the parts actually are. Well, first of all, you can only have one number in front of the decimal point. So if here's the decimal point, there can only be one number in front of the decimal point. That number cannot be 0 in true scientific notation. Now, you can have as many numbers here. You can have just one number, right? Or you can have 2 numbers, 3 numbers, 4 numbers, 5 numbers. This section up front here, this entire section, is called the mantissa, or coefficient. And this will come up in a later video about significant figures. I'll just mention it right now. All of the numbers in the mantissa are significant figures, including any zeros that appear in the mantissa. All right, so again, only one number can be in front of the decimal point. There it is, the number 3. This entire section in front of the multiplication sign is called the mantissa, or the coefficient. All of the numbers in the mantissa are significant figures. And again, this will come up in a later video about significant figures. Now, this part over here, either the 10 to the 14 or the 14, however you want to look at it, is called the exponent, or the order of magnitude. And this literally means 10 raised to the 14th power. Now, for example, if this was 10 to the 2nd power, it would be times 100. If this were 10 to the 3rd power, it would mean the mantissa times 1,000. All right, this is literally some math going on, some multiplication going on. That is the literal meaning of this scientific notation. And again, the 3 parts, right? One number in front of the decimal. The whole beginning is called the mantissa. And the 10 to the 14th or the 14th, this part after the multiplication sign, is called the exponent or the order of magnitude. Now, just a quick check, which of these 6 numbers are in correct scientific notation, based upon the fact that only one number can be in front of the decimal. All right, this one here, only one number in front of the decimal. So this one is in correct scientific notation. This one here has 2 numbers in front of the decimal. This is not in correct scientific notation. This one doesn't have a decimal. So again, not correct scientific notation. This one does not have a number in front of the decimal. This is not correct scientific notation. Okay, this one number in front of the decimal, correct scientific notation. And finally, this one number in front of the decimal, correct scientific notation. All right, so please remember, it is only considered correct scientific notation if there is exactly one number in front of the decimal. It doesn't really matter if there's no numbers or how many numbers there are after the decimal, but there can only be one number in front of the decimal. Okay, so for a quick little introduction into changing decimal numbers into scientific notation, for our purposes here, a big number or a very big number is going to be considered 1 or greater. Now, big numbers are going to require positive exponents in scientific notation. The other possibility is an exponent of 0, like right there, 10 to the 0 power. All right, so let's take a look at these decimal numbers, these big numbers, and how they convert into scientific notation. All right, the number 7, all right, is going to be 7 times 10 to the 0 power. What does that translate into mathematically? Since 10 to the 0 power is 1, then this represents 7 times 1, which is 7. Here we have 5,000. That would be in scientific notation 5 times 10 to the 3rd. Remember that 10 to the 3rd is 1,000. So what you're really seeing here is 5 times 1,000, which is 5,000. Down here we have 5,070,000. In scientific notation, this would be 5.07 times 10 to the 6th. 10 to the 6th is 1 million. And if you plug into your calculator 5.07 times 1 million, you're going to get 5,070,000, just like this. All right, so to summarize here, big numbers, or very big numbers, that's going to be 1 or greater, will have exponents, either 0 or most of them positive. 10 to the 0, 10 to a positive number, 10 to a positive number. All right, big numbers are going to have positive exponents. Keep that in mind. Now, for our purposes, small numbers will be defined as numbers less than 1. Numbers less than 1 are going to require negative exponents. So here's a decimal number, 0.244, and that in scientific notation would be 2.44 times 10 to the negative 1. You see that a number less than 1 gets a negative exponent. Now, what does that literally translate into? What the math that you're actually doing here is 2.44 times 0.1. 10 to the negative 1 is 0.1. 2.44 times 0.1 is 0.244, just like the original decimal. Here we have 0.00389. In scientific notation, that would be 3.89 times 10 to the negative 3. Again, a number less than 1 requires a negative exponent. What's the math that is actually occurring here? You're taking 3.89, multiplying it by 10 to the negative 3rd, which is 1,000th. Remember, that would be the 1/10th, 100th, 1,000th. And if you multiply 3.89 times 1,000th, you're going to get 0.00389. All right, so this is the same as this, is the same as this. This is the same as this, is the same as this. Excuse me. Remember that small numbers, less than 1, will get a negative exponent when converted into scientific notation. So here's an example of a really big number from chemistry. This is 6.02 times 10 to the 23rd objects. It's also known as 1 mole. So in that way, it's similar to, for example, 1 dozen or 1 gross, where it's a word that means a certain number. So 1 dozen would mean 12 objects. 1 gross would be 144 objects. 1 mole is this many objects. Now, how do you write this in decimal form? It's 602 and 21 zeros. All right, 7 groups of 3 zeros. Now, let's look at, well, okay, I'm sorry. This is called Avogadro's number also, this number in chemistry. Let's look at how we would name a number like this. All right, right here, this would be the thousands place. Right here, this would be the millions place. Right here is billions. Right here is trillions. The trillions place. Here is the quadrillions. Quadrillions place. Here is the quintillions. Oops, spelled that wrong. The quintillions place. And right here, which will help us name this number, is the sextillions place. Yeah, that's a real word. Crazy, right? So this number, Avogadro's number, is 602 sextillion. All right? Now, how would we convert this number? Because we don't want to be writing all these zeros. How would we convert this number to a decimal? To scientific notation, to this. Well, first of all, there's as an implied decimal over there, an imaginary decimal, an implied decimal. So you put in the implied decimal where it should be. And now we start jumping places until only one number is in front of the decimal point. So here we go. All right, jump. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 jumps, or 23 decimal points, to move the decimal from there to a place where there is only one number in front of the decimal. Now remember, we counted 23 jumps. That means that to write this number, Avogadro's number, in scientific notation, you would write 6.02 times 10 to the 23rd. So we just converted this number, this decimal number, to scientific notation. And remember, there can only be one number in front of that decimal when you stop jumping. All right, so this again is an example of why you would use scientific notation. You don't want to write this number. It's much easier to write this number in scientific notation. So we figured out that this number is 602 sextillion. And again, it sounds really funny, but that's how you say it. Now, these designations up here are a little different in Europe. So be careful if you're speaking to somebody from England or Germany, right, or maybe Italy. They use slightly different words up here. They kind of rearrange them a little bit. So please be careful if you're speaking to a scientist or a mathematician in Europe. So I'd like you to look on your physics reference tables. I'll show you a copy right here, and I'll also show you where you can download them from. And I'd like you to look up two big numbers. All right, the distance from the Earth to the Sun is going to be on the front page of the reference tables, and also the number of elementary charges in 1 coulomb is going to be on the front page of the reference tables. Well, we'd like to convert these numbers to to scientific notation because there's too many zeros. We don't want to be writing all these zeros. All right, so there would be an implied decimal. This is the unit meters. All right, there's the unit meters. So it's 150, let's see, 1,000, million, billion. Okay, so it's 150 billion meters from the Earth to the Sun. Now, your implied decimal point goes right there. Your implied, your imaginary decimal point. And we're going to jump until there's only one number in front of the decimal point. We're going to jump the decimal point to here and count the number of jumps. That will be the exponent. So here we go. Jump. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So now the decimal point is here. That means that in scientific notation, the distance from the Earth to the Sun in meters is 1.50, all right, times 10 to the 11 meters. All right, now actually, the way this is written, we would just put 1.5. What's going to happen is in a later video where we discuss significant figures, I will talk about how you know whether to put 1.5 here or 1.50 or 1.500. It comes up under significant figures. All right, but for now, if you put 1.5 or 1.50, we're not going to care that much as long as you get the decimal, the exponent, correct. All right, now, the number of elementary charges, for example, the number of electrons that would be in 1 coulomb, right, would be, okay, now here, we've got 1,000, million, billion, trillion, quadrillion, quintillion. So this is 6 quintillion, 250 quadrillion electrons. So we're in the quintillions here. 1,000, million, billion, trillion, quadrillion, quintillion. Approximately 6 quintillion electrons. So 6 quintillion, 250 quadrillion electrons. Let's change this to scientific notation. Our implied decimal is right there. We are going to jump until there's only one number in front of the decimal point. So we're going to jump to here and count the jumps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 jumps. So this number in scientific notation would be 6.25 times 10 to the 18th, and in this case we're saying it would be electrons. All right, 6.25 times 10 to the 18th electrons. So this demonstrates again how to convert a decimal number into scientific notation. If you don't have a decimal point, you put your imaginary decimal point or your implied decimal point at the end. You jump until there is only one number in front of the decimal point. Then you write your numbers here, right, times 10 to the number of jumps was 11. It's positive, the exponent is positive because it's a big number, 1 or greater. This was 18 jumps, it's positive because this is a big number, 1 or greater. Very, very simple to convert decimal numbers into scientific notation. Now we have two very small numbers. This number is found on the first page of your physics reference tables. This number is found on the 4th page on a chart that says resistivities. All right. So let's convert. I mean, we don't want to be drawing all these zeros, and there's a good chance you would put the wrong number of zeros anyway and make a mistake. So let's convert these to scientific notation so we don't have to be writing all of these zeros. All right, so here we go. There's a decimal point right here. All right, so we're going to count the number of jumps until there's only one number in front of the decimal point. So we want the decimal point to end up right there. So here we go. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 jumps. Since this is a very small number, a number less than 1, the exponent is going to be negative. That was 11 jumps, so the exponent will be negative 11. So we've got 6.67 times 10 to the negative 11. And the unit for the universal gravitational constant, again, found on the first page of your reference tables, is Newton meter squared per kilogram squared. Don't worry too much about the name of the number or the unit right now. We're focused on converting the decimal into scientific notation. You'll learn about the name of this number and this unit later in the course. All right, now, this one is the resistivity of aluminum. We want the decimal point to end up here. The number is obviously less than 1, so it's a very small number. It will become a negative exponent. Let's count the jumps. 1, 2, 3, 4, 5, 6, 7, 8 jumps. So this number in scientific notation will be 2.82 times 10 to the negative 8. And the unit here is ohms times meters, or ohm meters. All right, and again, let's not worry about the name of the number or the unit right now. You'll learn about that later in the course. Our focus right now is on converting decimal numbers to scientific notation. Now that we've gone through a few problems converting decimal numbers to scientific notation, let's go over what the rules would be based upon what we've done. Rules for converting decimal numbers to scientific notation. Okay, the first thing we did was we looked at the decimal number. If there was no decimal point shown, then we put an implied decimal point at the end. Number 2, we decided if the number was 1 or greater, in which case it would become a positive exponent, or if the decimal number was less than 1, in which case we knew it would become a negative exponent. The third thing we did was to move the decimal point and count the number of jumps until only one number was in front of the decimal. And then finally, the fourth thing that we did was to write the number in scientific notation. And again, the number of jumps becomes the exponent. If the decimal number was 1 or greater, then the number of jumps becomes a positive exponent. If the original decimal number was less than 1, then the number of jumps becomes a negative exponent. All right, so you might not need a bunch of rules. You might just be able to do it. But if you ever run into a problem where you're not sure how to convert a number from decimal to scientific notation, or maybe you forget, come back to the rules and follow the rules one at a time until you get the hang of it again. After a while, you won't need rules. You'll just know how to do it. Now let's practice using the rules that we set forth. Here, we do not see a decimal. This is the number 700, so there's an implied decimal here. Now, I also want to have one little note down here in terms of significant figures. And if your teacher covers significant figures, you can look on one of my videos which specifically relates scientific notation to significant figures. Right? It's in a later video. Right? I'm just going to mention one little rule to help you out for now. For now, if you see a decimal, in other words, if there's already a decimal, this one does not have a decimal at the moment. If you see a decimal, you're going to keep the zeros at the end. So here I see a decimal, I'm going to keep those 2 zeros. Here I do not see a decimal, so I'm not going to keep those 2 zeros. All right, so let's follow the rules. All right. Rule number 1, look for the decimal. There's no decimal, so I'm going to put an implied decimal. All right. Now I'm going to jump 1, 2. All right, now since this number was 1 or greater, it's going to be a positive 2. The exponent will be a positive 2 for 2 jumps. So this is going to be 7 times 10 to the positive 2. Note, since there was no decimal at the beginning, I did not put the zeros. Now watch. There is a decimal here. So now I'm going to jump 1, 2. All right, so this is going to be 7. Since I saw a decimal, if you see a decimal, keep the zeros at the end. All right, so 7.00 times 10 to the positive 2. All right, this one does not have a decimal. All right, so I don't see a decimal. I'm not going to keep the zeros. I'm going to put my own decimal. All right, and it's going to be 1, 2, 3 jumps. All right, remember, you jump until there's only one number in front of the decimal. So the decimal is going to end up here, and that's going to be 7 times 10 to the positive 3 jumps. All right, here we go with the number 9. I do not see a decimal, so I put my own implied decimal. I do not have to jump, so the jumps would be 0. 0 jumps. So this would be 9 times 10 to the 0. This one here, I see a decimal. As a matter of fact, this number is the first number we're doing that's less than 1. This one is going to have a negative exponent. I jump 1, 2. There, I see a 0. I see a decimal, so I keep the zeros at the end. So this one is going to be 9.0 times 10 to the negative 2 jumps. This number was less than 1, so it's a negative exponent. I jumped twice, so it's a negative 2. This one here, all right, I see the I see the decimal, so I'm going to keep the zeros at the end. I'm going to jump once. The original number, less than 1, so this is going to be a negative exponent. 1 jump, negative 1. 9.00 times 10 to the negative 1. The number 27. I don't see a decimal. I know that the decimal would be here, so I put it there. I jumped once. This number is 1 or greater, so it's going to be 2.7 times 10 to the positive 1 jump. Okay? This one here, I see a decimal, so you keep the zeros at the end. There are no zeros at the end. So I'm going to jump 1, 2, 3. And this is going to be 2.7 times 10 to the negative 3. This was a number less than 1, so the exponent must be negative. Here, there's no decimal. I put my own decimal. I'm going to jump. So there's only one number in front of the decimal. 1, 2, 3, 4 jumps. The number is 1 or greater, so this is a positive 4. 2.7 times 10 to the positive 4 power. Here we have the number 40. I don't see a decimal, so we're not going to keep the zeros. All right, I put my own decimal. I jump once. It's a number 1 or greater. That 1 jump is going to become a positive 1 exponent. So it's going to be 4 times 10 to the positive 1. I did not see a decimal at the beginning, so I do not keep the zeros. I do not keep the 0 at the end. All right, here. I see a decimal, so I'm going to keep this 0 at the end. All right, I jump once. So this is going to be 4, keep the 0, 1 positive jump. Okay? And finally, over here, I see a decimal. I'm going to keep the zeros at the end. All right, not these zeros. The zeros at the end. Okay? So I'm going to jump 1, 2, 3 times. 3 jumps. The number is less than 1. So it's a negative exponent, negative 3. So this is going to be 4.00 times 10 to the negative 3. All right, now, you're going to need to practice. You're going to need to practice, practice, practice. Really, that's how you get good at math. You practice. That's really how you get good at anything. But math especially, you're going to have to practice, practice, practice. Go through the rules. Keep a copy of the rules where you can look at them. Jot this rule down. Make sure you have this rule also. All right, keep all the rules handy. All right, and practice, practice, practice. There's plenty of practice problems, all right, on the accompanying worksheet. Again, just a quick little note about the relationship between scientific notation and significant figures. All of the numbers in the mantissa being the beginning here in front of the multiplication sign, all of the numbers in the mantissa are significant. So here in this number we have 1, 2 significant figures. This would be 2 sig figs. Here we have 3. 1, 2, 3 significant figures. Remember, all of the numbers in the mantissa are significant. Here we have 1, 2, 3, 4 significant figures. 4 significant figures. And here we have 1, 2, 3, 4, 5 significant figures. Again, there will be an entire video devoted to the relationship between scientific notation and significant figures, but you can just remember this for now. It'll help.